Good morning. Today we're going to be going over notes on waves. So we started an introduction last week on harmonic motion. A lot of the vocabulary terms you're going to see are repeated, which is why we went over those notes first. So if you have not reviewed the video on Edpuzzle on harmonic motion, please review that video first before continuing along with this Edpuzzle video. Waves. Oops. Okay, so we talked about in our notes for harmonic motion how motion appears in cycles. So remember, you have linear motion, okay, and then you have harmonic motion. So linear motion is not something that repeats. You can say it's motion in a straight line. So let's say you're talking about taking a drive from here to McAllen. Okay, you might not take the same route every time. That would be considered linear motion. Anytime motion repeats itself, that's known as harmonic motion. So let's say the hands moving on a clock, or the swinging of a pendulum, or the spinning of a tire. Okay, those would all be examples of harmonic motion because it's the same motion repeating itself over and over and over. Nothing about the motion is changing. Okay. Here they're telling you that the motion of the bicyclist can be both linear and harmonic. So let's say if you're talking about him taking a drive on his bike around the city. Okay, he's not going to take the same path every single time, so that could be considered linear motion. But the motion of the wheel on the bicycle turning, that would be an example of harmonic motion. His pedaling of his feet, that would be considered harmonic motion. Remember one cycle. So what is a cycle? For one cycle would be one over and back, so one back and forth motion, so it would be one complete turn of the bicycle wheel, or it would be one complete back and forth swing of the pendulum. If you're talking about the girl on the swing, it would be one complete back and forth motion. If you're talking about the hands moving on a clock, it would be the hands going around one complete time. So a cycle is a unit of motion that repeats over and over, and it's just one back and forth motion of that particular motion that it's doing. Okay, remember we talked about oscillators. So oscillators are any objects that perform harmonic motion, or the same repetitive motion over and over and over again. We talked about the period and the frequency. Remember, the period is the time in seconds that it takes for one cycle to occur. So if you're talking about the swinging of the pendulum, it would be the amount of time in seconds for the pendulum to swing once back and forth one time. That would be one complete cycle. Some people get it confused. So here's where the pendulum starts. Here, when it reaches back to the same position, that would be one cycle. Not over here. This would be half a cycle. So at this point here, the pendulum has completed half a cycle. It's not completed one whole cycle until it goes back to the place where it started. Okay. Again, period is the time it takes to do that, and you're looking at the time in seconds. The frequency, remember, the frequency is the number of cycles per second. Okay, so if this pendulum were swinging fairly fast, okay, you would be looking at how many back and forth motions it can do in a 1 second time period. So the pendulum would have to be going fairly fast in order for it to have more than one cycle per second. We measure frequency in hertz. So another way that you can write hertz would be cycles per second, but just remember that a cycle per second, one cycle per second, is 1 hertz. We talked about amplitude. Okay, so remember, amplitude is the size of the cycle. If you're looking at a pendulum, this would be the amplitude here, so how far from its equilibrium. So equilibrium is when there's no energy put into the object itself. So if there's no energy being put into the pendulum, it's not going to swing. It's just going to stay hanging straight down. Once you add energy to the pendulum, it's going to start to swing back and forth. The more energy you put, the harder you swing it, the further out from this equilibrium point it's going to be, the bigger the amplitude is. So the amplitude would literally be this measurement of the distance of how far it is from its equilibrium. So here's a small amplitude, and then here is a bigger amplitude. So you can see that the distance from the equilibrium is greater. If you're looking at a wave like this, which is what we're going to do today, this midpoint right here, okay, that would be when there is no energy put into the wave itself. Once you start putting energy in, the wave is going to start to move. The more energy the wave has, the further out from the equilibrium that wave is going to be. So you would measure the amplitude from its equilibrium point up until its furthest point. So either up this way or down this way, same difference. We're going to be looking at what each individual part of the wave is called. But again, the amplitude, okay, how far from its equilibrium, is how much energy the wave has. Okay. Damping, just so you know, damping, okay, if you ever just were to swing a pendulum, or if you ever swung on a swing before, you know that you have to keep putting energy in. If you're on a swing, you have to keep pumping your legs back and forth to give you that energy to keep you going, or to help you with the momentum. Once you stop putting energy in, okay, it's going to slow down. Your amplitude is going to start to get smaller and smaller and smaller until it eventually stops and you're back at your equilibrium. That's called damping. The reason that occurs is because the energy is decreasing due to friction. In this case, you're talking about friction with the air. So same thing, if you were to swing a pendulum, if you just put something heavy on a string and you were to swing it and stop swinging it, you are not putting any more energy. It'll continue to swing for a bit, but you're going to notice that the amplitude is going to get smaller and smaller and smaller until it eventually stops. That's called damping. Okay, we looked at these formulas last time, so remember they're inversely related, the period and the frequency. Okay, period is the amount of time it takes to complete one cycle. The smaller the period, so the less time it takes, the bigger the frequency is going to be, the more cycles you're going to see in a 1 second time period. So if you're talking about a pendulum swinging, right, the faster the pendulum is swinging, the less time it takes for it to complete one back and forth motion, the more cycles you're going to see in a 1 second time period. So they're inversely related. These are the formulas that we used to calculate period and frequency. So remember, period is 1 divided by the frequency, and frequency is 1 divided by the period. The units for period, remember, period is the time it takes to complete one cycle, and we measure that in seconds, and the frequency is the number of cycles in a 1 second time period. So go ahead and solve for questions 1, 2, and 3. Okay, waves, so which is what we're going to be talking about today. So waves is an example of harmonic motion. Okay, waves is the same motion repeating itself over and over and over again, and it's traveling energy, so it's carrying energy with it. There's two different types of wave that we're going to be looking at. We're going to be looking at mechanical waves, and we're going to be looking at electromagnetic waves, or EM waves. Okay, the difference between these two is that mechanical waves need matter or a medium in order to transfer their energy. A medium is anything that has molecules, liquid, solid, gas. Okay, it needs to travel through something that has molecules in order to be able to transfer its energy from one place to another. Sound is an example of a mechanical wave. Without air molecules, or molecules in a solid or in a gas or in a liquid, sound would not be able to travel from one place to another. Whereas light is an example of an electromagnetic wave. Light can travel through nothing at all. It can travel through solids, liquid, gases because it has the molecules, but it can also travel through nothing at all. So mechanical waves needs the molecules, it needs a medium in order to transfer its energy from one place to another, and electromagnetic waves do not. So this is just reinforcing the fact that, again, mechanical waves, like sound, need molecules. It needs to travel through a medium in order to transfer its energy. So these are the two different types of waves, okay? And you can see that there's a big difference in how they move. So this right here, this is what people usually think of when they think of waves, okay? Ones that go up and down and up and down. These are example of transverse waves. Okay, and then you have these are examples of longitudinal waves. Okay, this is the way light travels. So light travels transversely, it travels up and down, whereas sound travels longitudinally, it travels like this. Okay, so transverse waves, here you have, okay, the wave going up and down. If you were to look at the energy itself, the energy is only moving side to side, so energy is moving from left to right or right to left, but the wave itself is going up and down. So they form a 90-degree angle. So you have the energy moving side to side, but you have the actual wave itself moving up and down. So it's forming a 90-degree angle. Okay, and then the longitudinal waves are also known as compression waves. And so what's happening here is you have energy, again, moving side to side, but what it's doing is it's pressing molecules together. And then as the energy passes through those molecules, the molecules start to spread back out, where the second wave of pressure or energy will push those molecules back together. So you have a constant flow of high energy where the molecules are close together to an area of low energy where they're more spread apart. So here you can see it a little bit better if it was on a slinky. Okay, you have where the energy is traveling through the molecules itself, they're going to be pressed together. That's an area of high pressure or compression. And then you have the area of rarefaction for where they're spread apart, the molecules are spread apart, there's no energy flowing through there. Okay, in terms of wavelength for each of these, okay, so for transverse waves, and I'll go back and forth through the slides. For transverse waves, okay, you have different parts to the wave itself. Here, the top part of the wave would be called the crest. The bottom part would be called the trough. If I were to draw a line right in the middle, so like this, that would be its equilibrium. So this is when no energy is flowing through the wave itself. Once energy starts to flow through the wave is going to start to move up and down. Remember, that's how transverse waves move. They move perpendicular to the energy itself. So energy is flowing left to right or right to left, and the wave itself is going up and down. So when there's no energy flowing through the wave, it would be a straight line. Once energy starts to flow through it, you can see the wave itself going up and down. The more energy flowing through the wave, the higher up the wave is going to be, the bigger the amplitude. So this top part of the wave is called the crest. Okay, and the bottom part is called the trough. If I'm looking at one cycle for a transverse wave like this, that's known as a wavelength, the actual length of the wave. Okay, and you would measure from crest to crest or from trough to trough. It's really any two same points, so I could pick any two corresponding points on a wave. So if I were to pick this point right here, okay, that same spot on the very next wave right here, that distance between those two spots, that would be a wavelength. That would be one cycle. It's just easier to do it from crest to crest or from trough to trough. So when you're looking at the wavelength, okay, we designate wavelength with the Greek letter lambda. It looks like an upside down letter Y. Okay, that is the length of one wave. So you're actually measuring the distance of a cycle. So either from crest to crest or from trough to trough. Remember, one cycle for a transverse wave would be a wavelength. Okay, the length of that particular wave. So remember, you have the top part is the crest, bottom part is called the trough. The one cycle would be one wavelength, and so you either measure the distance from crest to crest, trough to trough, or any two corresponding points. So I could pick this point, and that would be this point on the very next wave. Okay, frequency, remember, would be the number of cycles per second. So if I'm talking about this particular wave here, I'd say I'm starting here. Okay, from here to here, it's 1 second, and I have 1, 2, 3 cycles in this 1 second time period. So this particular wave would have a frequency of 3 Hertz. And then you can go ahead and solve for the period, the time that it takes to complete one cycle, so the time for the wave to go from here to here, and that would just be 1 divided by 3 because the frequency is 3, so 1 divided by 3 would be the period, the time that it takes to complete one cycle. For mechanical waves, okay, mechanical waves, you would measure the same thing. So this would kind of be like the crest. This would be the trough. So you would measure from crest to crest, or from area of compression to the next area of compression. So for a longitudinal wave, it would be one area of compression, one area of refraction. That would be a wavelength. So that would be one cycle. Remember, we're talking in terms of energy. Okay, so for transverse waves, energy would can entail two things. The higher the frequency, or the bigger the amplitude, the more energy the wave is going to have. So the faster the wave is going, the more cycles you see in a 1 second time period, the more energy the wave is going to have. And then simultaneously, the bigger the amplitude, the more energy the wave is going to have. Okay, thank you for paying attention today. I hope you guys are doing well. Please email me if you have any questions.